Okay, hello everybody, welcome to the Alkyne review video. This is the last review video before your exam 2. So without further ado, let's kind of just jump right into this. So alkynes. So again, we're going to be talking about alkynes in the context of them acting as nucleophiles in reactions. You can imagine that they would react similarly to the alkenes we saw in the last chapter. The only nuance here is that we have an additional pi bond present. So instead of one sigma bond and one pi bond, we should have one sigma bond and two pi bonds in these functional groups. So a brief introduction to alkynes. Here's a generic example of an alkyne, where R denotes any generic substituent. They could be protons, they could be other alkyl groups. Just some things to keep in mind. Remember, the carbons of an the carbons of an alkyne are sp hybrids. Sp hybrid carbons. That means that they have 180-degree geometries around them. Notice 180-degree geometry. Everything is linear. Okay. And more specifically, this triple bond in between, is one sigma bond comprised of the carbon-sp bond overlap. And then one pi bond is the carbon perhaps 2px with carbon 2px overlap. And then the other pi bond is perhaps maybe the other available p orbitals, perhaps carbon 2py with carbon 2py. Remember, those x's, y's, or z's are arbitrary. We just have to have them align in 3D space. Okay, so without further ado, let's kind of talk about something called an acetylide anion. Okay, so here's a generic alkyne. We know the hybridization, we know the bonding pattern in these things. But remember, we also talked in the acid-base chapter, if we have a terminal alkyne, so perhaps something that looks like this. This is terminal because we have a proton here. There's nothing that could come beyond that, so we would call this a terminal alkyne. And we said that these sp, protons, so this is in sp, protons, are acidic. If you remember, that was the trend that we talked about where, if we had a generic, sp3 versus sp2, versus sp, so sp3 center, sp2 center, sp, we said, in terms of stability, the anions, so the pKa increases here, the pKa decreases here, okay, or the Ka is higher, meaning the acidity is higher with more S character. Our rationale back then was, more S character is essentially the same as saying more electronegative, so obviously a negative on a more electronegative thing is more stabilized, okay? So again, just to put some numbers to this, the pKa of, an sp3 proton is probably around 50, or somewhere around 35 for alkenes, and then for the sp, remember, it's around 25. Okay, so we can exploit the acidity of these protons of terminal alkynes to do various substitution reactions. So let's kind of see that. So, here again is that generic structure. I could perhaps take a base like sodium amide. Okay, that base is sufficiently strong enough to deprotonate the proton. Remember, protons only like one bond, so we exceed the octet. That carbon retains the electron density of the starting bond. And the result is what we call an acetylide anion. And obviously, neutral ammonia. Okay, so just to put some numbers in, the pKa of a terminal alkyne is around 25. The pKa of the other acid on the other side, the ammonia, is about 35. And remember, the equilibrium always lies towards weaker acid. Basically saying that we could form that acetylide anion. This is an acetylide anion. Okay, it's the result of deprotonating a terminal alkyne. These are pretty good nucleophiles, so I just want to write that in, baby. Good nucleophile. So we'll see that below in various substitution reaction. Okay, so before we see them react in various substitution reactions, let's kind of just talk about alkyne nomenclature. You could be asked various questions, so we just need to be aware of the nuances here. So alkyne nomenclature. Okay, so again, Everything is the same as we saw with alkene nomenclature, except here the alkyne takes priority. Again, we want to number through the alkyne bond, and we want to give it the lowest possible set of numbers. Again, we could have multiple triple bonds where they could be a diene or a triene, so just don't forget those things. And we could even have an alkene and an alkyne present. Those are called anions, okay? So kind of a lot of things to talk about here. So let me just do some examples. Okay. So if I had this, for instance, okay, so the numbering would be, obviously we want to go through the triple bond, we want that to be encountered first, and we obviously want to number the longest carbon chain. So how we would do this is 1, 2, 3, 4, 5, 6, 7, that's the only numbering scheme possible. Since this is a terminal alkyne, I don't have to necessarily indicate where the position is, but I always do. You know, more here is not, I guess, bad. I tend to always do that just to be specific. So where is the position of the substituent? Well, 6, there's a methyl. The parent chain is hept. Where is that alkyne? At 1. And obviously we would end it in yne, Y-N-E. Pretty simple for that first molecule. Okay, let's try another one. So if I had a crazy molecule that perhaps looks like this. Okay, to me it's obvious to start from the right side versus the left side, because if I started from the right side, my first alkyne's at 1 versus a 1, 2. Okay, so clearly we want to start from the right. If I number through the carbon chain, it'll be a series like this. Okay, and then what is the substituent at 3? Well, it's 3 isopropyl. What's the parent chain? Hex. Okay, here's the nuance. When there's multiple of these pi bonds, like multiple alkynes, we have to add an A. These would be a diene, a triene, etc. You need to have an A. Where are they? Where do they start? Well, 1, 4, and then here is where you would say diene. Okay, so don't forget the A. That's kind of a nuance there. Let's do an example of an anion, okay? So perhaps, you know, something where we have to consider easy geometry. Okay, so again, the alkyne priority here. So we start 1, 2, 3, 4, 5. I don't think we have to do the whole easy depiction, but you could see that that's clearly an E alkene, so let's put an E here. Okay, so remember that goes in the beginning of the name. There are no alkyl substituents, so we can go right to the parent names. This would be pent. So this is not a diene or a triene, so we don't need the A, but now we need to indicate the positions of everything. So we would say pent hyphen 3 hyphen N hyphen 1 hyphen yne. Okay, N-yne. N always gets named before the yne. Okay, so that's where we are. Can we do any more? I think that's good enough. Okay, so just make sure that those are the new kind of rules that get addended. If there are multiple triple bonds, you have to add the A, and then always there's the N-yne situation, but I don't think there's anything crazier there. Okay, so back to this idea of acetylide anions acting as nucleophiles. So they can participate in a substitution reaction. We're going to talk a lot more about this specific nature of this substitution called an SN2 in subsequent chapters at the end of the semester, but for all intents and purposes, let's just kind of draw this depiction. So remember, we had the anion that resulted from, you know, I guess deprotonating with sodium amide. So remember, there's the counter ion there, not really important. But if I had a generic, you know, alkyl halide, like perhaps, you know, bromoethane like this, you could imagine that there is a localized dipole moment towards the bromine that makes the carbon adjacent to the halogen electrophilic. So our nucleophile, that carbon. Our electrophile, this carbon. This will be the first reaction that we see that we actually extend the carbon chain. Very useful in synthesis at an organic one. So keep that in mind. So remember, it's always source to sink, but we exceed the octet at this carbon. Remember, there's 2 proton bonds there. So we must break the bond. And remember, it makes sense that that sigma bond density is retained by the bromine to form a anion. Okay, there are limitations to the types of, you know, haloalkane starting materials, this guy, that we can start with. Typically, we have methyl halides or primary and perhaps secondary, but these are by far the best, the methyl and the primary. So the result is now an extended carbon chain. Notice if I number the carbons, 1, 2, I should add now 1, 2. So there's 3, 4. This was the 3, the 4. So it's our first reaction where we're actually extending carbon chains. Let's see another example of this. This is by far a very, very useful reaction in organic one. We don't have many carbon-carbon bond-forming reactions available to us in organic one, so definitely be aware of this. So you might see, a starting terminal alkyne, some sort of base, so sodium amide, and liquid ammonia. Ammonia is the solvent there for step 1. And then step 2, we could have perhaps a methyl, iodide, molecule. So again, we could imagine the NH2. It's a base. This is just an acid-base reaction. That's why we started with this at the beginning of the semester. We now have an acetylide anion. Remember, there is a localized dipole moment towards the iodine, which polarizes the carbon to be our electrophile. The nucleophile can attack the methyl. We exceed the octet, so we must break that carbon halogen bond. It gets retained by the halogen. And we have now effectively extended the carbon chain of that starting material by 1. So you would see perhaps something like this. 1, 2, now 3, where we had 2 carbons before. That third came from the methyl. Okay, so pretty nice reaction. Definitely know how to do this. Okay, that's step 1. Reaction 1 of, maybe I should write this here. Reaction 1, this was acetylide addition. Okay, so just be aware, it's step 1 is a deprotonation acid-base. We know why sp protons are acidic back to the beginning of the semester. And then step 2 is this, what we call nucleophilic substitution. We'll come back to this at the end of the semester. This is called an SN2. So just be aware of that. We'll come back to SN2. That's step 2 of this acetylide addition. Okay, reaction 2. Reaction 2. So just as we saw halogens adding across double bonds, we can imagine that they add across triple bonds. We could also remove halogens from haloalkanes to form these double or triple bonds. So the first thing we're going to talk about is this thing called double dehydrohalogenation. Okay, so this is a means to prepare alkynes, okay, from a dihalide. Okay, so specifically, if I started with something like this, R and R prime, just to denote they could be different things. Okay, so notice that this is a dihalide. The X's refer to halogens. They're drawn in this arrangement for a reason. I will allude to that later. But this is a dihalide starting material. You can imagine if I had my base, same base present. More specifically, if I write 2 equivalents, meaning there is 2 for every 1 starting material, I could prepare an internal alkyne. Okay, so how do we do this? Okay, so let's kind of talk about mechanistically, how does this happen? This is stepwise, so there should be an intermediate. So step 1 from 1 equivalent forms something, and then another equivalent forms that total, internal alkyne. So let's kind of break this mechanistic picture down. So maybe it would be helpful if I could just copy and paste this. Nice. I don't really know how to do that. I'm just going to redraw it. Okay, so if we started with this, and let's show the first equivalent. So NH2 minus. I don't care about the spectator ion. You can imagine that the first equivalent, going to deprotonate a proton, donate that electron density in to form a double bond, facilitating the removal of the halide. Something like that. So that would form an alkene. Okay, so 1 equivalent forms an alkene. You can imagine that the same thing happens with another equivalent. But since there's an alkene already present, we would call that an alkyne once we form an extra pi bond on top. So you can imagine deprotonate, facilitate the removal, and this forms that internal alkyne. Okay, so just be aware, if we start with a dihalide and I use 2 equivalents of base, I could eventually get to the alkyne. I could ask you on the test, what happens if I just had 1 equivalent of base? You would want to draw this structure, okay? And then if I said 2 equivalents or a subsequent equivalent, you would expect that structure, the alkyne, okay? So remember, how do we form a dihalide? So just to keep these things in mind, we should know how to make that from an alkene. And remember, that was the simple bromination reaction with like DCM. Remember that could form that halonium ion bridge. Let me just kind of bring your attention back to this. It could form that, bromonium, intermediate, and then the other bromine anion attacks in a mechanistic fashion from the back face that we had anti-addition. This is the dihalide I'm talking about. We could then take that dihalide, use 2 equivalents of the sodium amide in liquid ammonia to get a terminal alkyne. Okay, so just keep in mind all these things are related. All right. Okay, maybe I'll give you one example with an actual, atoms on it. Okay, so if I had this, right, step 1, NaNH2, NH3. Okay. All right. Let's do that. And let me do 3 equivalents. Okay. So I'm going to draw in protons just for, clarity. Again, first equivalent of sodium amide, deprotonates, comes in, ejects the bromine. So we should form an alkene. Between, let's just number, 1, 2, 3, 4, 5. So between 4 and 5. 1, 2, 3, 4, 5. There should be an alkene there. And remember, at 4, we had a bromine. Okay? Then you can imagine the next equivalent of NH2. This is equivalent number 2. Deprotonate, donate in, ejects the bromine. So again, 1, 2, 3, 4, 5. So 1, 2, 3. 1, 2, 3, 4, 5. Actually, sorry, do that bad. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so if I only used 2 equivalents, what ends up happening is there's this weird nuance. Sometimes in textbooks they write 3 equivalents, which seems redundant, but they add the protic source. They add a protic source just to add that proton back on. So my whole point is I just wanted to show you this. Sometimes you might see it drawn this way instead of 2 equivalents. So the 3rd equivalent, this seems redundant, but just be aware that it's sometimes drawn like this in the literature. It could deprotonate that terminal proton to form an acetylide anion. I know this sounds redundant. And then water from step 2 just acts as a quenching source to add it right back on. I just want to show this to you because some textbooks do it that way, and then you go back to just like that neutral terminal alkyne. But just be aware, sometimes they show 3 equivalents with a workup versus just 2 equivalents. So I just wanted to be aware. I want you to be aware of that. Okay, so we now showed that we can use acetylide anions to extend the carbon chain in an SN2 fashion. We saw we can take an alkene, form this kind of dihalide species, and then use 2 equivalents of base to form a terminal alkyne. Now there are several, electrophilic addition reactions we can do to the alkyne that we've seen with the alkene. For example, we can add bromine or chlorine diatomic species across to form something called a vicinal dihalide. So we'll see what that looks like right below. Okay, so this would be reaction 3. We're going to call this, I guess, reactions with X2. This would be like Br2, Cl2. Okay, so very interesting. Here the equivalents matter as well, okay? So we could have 2 different species based off of the amount of equivalents we use. So for instance, I'm just going to go right into the example. Actually, no, I'll just do this generic picture first. So if we had a generic internal alkyne, and I used 2 equivalents of a diatomic halogen, and maybe I used dichloromethane as the solvent, we should expect kind of this tetra-substituted divicinal halide thing. So vicinal just means 2 on the same carbon. So you could see 2 on the same carbon. That's vicinal. And there's like 2 of these, 2 sets of these, okay? But again, we could do this stepwise, where one equivalent of X2 gives us an alkene. Notice we have 1 equivalent adding across the triple bond, and then you could have 1 more equivalent of X2 to get there. So just be aware of these things. So let's do an example of that. Okay, so if we had perhaps an internal alkyne like this, and I have 2 equivalents of bromine and DCM, what would I expect? Well, let's do this mechanistically. So we have diatomic bromine. This double bond can grab the bromine, we exceed the octet, we must eject. So we form a bridged intermediate. Let's count how many carbons. There are 5. 1, 2, 3, 4, 5. The double bond was between 3 and 4. And you could imagine we have a very unstable intermediate where there's a carbocation actually on an sp2 carbon. You could imagine that one of the bromine lone pairs leans over to form kind of this bridge species. So this would be something that looks like this, very strained intermediate. And likewise, remember that bromine anion can come and attack either from the front or the back, because this is a planar molecule. So I'll do it like this. That swivels that bromine over. And we have now officially made kind of this dihalide around this alkene. Okay, so it's E, an E alkene here. But we did 1, this is the product of 1 equivalent. We could basically show that exact same mechanistic scheme one more time. This is just basically the last chapter of alkenes. So the pi bond can come here, attack the bromine. We form a very, again, even more strained intermediate. The bromine lone pair can lean over, form another bridge. So the intermediate is something that looks like that. And remember that anion we just generated can come in and form the other vicinal dihalide. You don't have to draw this mechanistic steps every time. I think it's pretty easy to predict the product. You would just remember to add 2 equivalents of bromine to each of the carbons of the alkyne. Something like that. So by that, what do I mean in a quick predict the product fashion? I'll just do this on the other page. In a quick predict the product, if I gave you this on the test. You would basically say I have 2 carbons here. So I would go 1, 2, and then each of those carbons gets 2 chlorines. It's that simple. Now, some people asked, during discussion before I, traveled, why don't the pi bonds in benzene react like they are alkenes? And there is a feature called aromaticity. We will talk about this when we get to the end of organic too, and there will be a lot of nuance about why those pi bonds don't react. But for all intents and purposes, if you see any of these pi bonds, do not touch them. Okay, leave them the way that they are. Okay, so that was preparation of kind of adding diatomic halogens across an alkyne. We don't just have to add a diatomic halogen. We could add just a hydrogen halide, such as HBr, HCl. So we would call this hydrohalogenation of alkynes. So we did 3. Number 4, this would be hydrohalogenation of alkynes. Again, this is going to be a equivalence situation that matters. So just to keep in mind, this is still Markovnikov addition, follows Markovnikov's rule. There are carbocations involved. Okay, so let's kind of just talk about this. So again, the generic picture of hydrohalogenation of an alkyne is if I have, perhaps this terminal alkyne, doesn't have to be terminal, but here's an example. And I show 2 equivalents of HX adding across this. You can imagine that this is 1, 2, from the 1, 2, you're going to get 2 halides adding on, okay, at the same carbon. So I think that's the key, is that the X's end up on the same carbon, okay? And so let's kind of see this mechanistically. So if I had, the cyclic structure with maybe a terminal alkyne sticking off, and I have one equivalent of HBr. So this is the first equivalent. Okay, so what happens? Well, the pi bond is going to grab the proton and form a bromine anion. So what does that look like? 1, 2, 1, 2. There's a double bond. Now, where would this carbocation go? Does it go at 1 or 2? Well, Markovnikov's rule says it should go at the more substituted position. And I'm just going to fill in, this is the proton that we just added. Maybe I'll just put like a little 1 there, H1, okay? So the proton went to the less substituted side, the carbocation formed at the more substituted side. That is Markovnikov's rule. Now, that anion from the step we just did is going to come back and attack the carbocation. And now we have kind of this, what we call this, vinyl halide species. So vinyl. Vinyl means directly attached to an alkene. So vinyl halide. Okay, now let's do one more equivalent. So HBr, the other equivalent. So again, I don't want you to memorize these things. Like, you should be able to predict how these things would react just by looking. So I see, okay, pi bond, probably going to grab the protic source. We're going to form a carbocation at the more substituted position. Okay, now we should have 3 protons here. So this was H1 from before. Maybe this is H2, and the one that was already present. We generated a bromine anion from the last step. You can see how it attacks that carbocation. And now we have kind of this vicinal halide structure. Something that looks like that. Okay, so pretty easy. I don't really have more on that. Okay. Of course, they don't have to be the same, I guess, equivalent. They don't have to be the same reagent. We don't have to do 2 equivalents of HBr. I could do 1 equivalent of HBr, 1 equivalent of HCl. So let's kind of see that. Another example. Okay, so you can imagine from the first step, I'm going to quickly go to predict the product here, but we have a 4-carbon chain, parent chain, so 1, 2, 3, 4. At 2 we had the methyl, 3 and 4 is where we had our kind of triple bond situation. 3 is the more substituted position of these options. So you can imagine that 3 is where, the first equivalent adds on to. And then once we add the second equivalent, so this is product of step 1. Once we add the second equivalent, you can imagine the bromine now comes on. Okay, so it doesn't have to be the same thing, all right? And this is a stereocenter, so just keep that in mind, that we could form stereocenters. Okay, so that is, I guess, adding diatomic species across an alkyne and adding hydrogen halides across alkynes as well. We also saw how we could dehydrate these dihalide species that were the result of halogenating alkenes to form these terminal alkynes. We also saw that we could take those terminal alkynes and do a carbon chain extension via the acetylide anion. So please be aware of all of these relations to each other. Okay, I'll take a break and we'll talk about the next set of reactions in a few minutes. Okay, so now we're going to talk about hydration of alkynes. Again, we saw acid-catalyzed hydration of alkenes, so you can imagine there's an acid-catalyzed hydration of alkynes. Likewise, we saw kind of this oxymercuration, demercuration of alkynes, so you can imagine, of alkenes, and you can imagine we're going to do that here with alkynes. And same thing with the hydroboration, you can imagine we're going to do that with the alkynes. So without further ado, let's talk about reaction number 5 of alkynes here. I'm going to call this hydration of alkynes. Maybe I'll call this 5A actually. This would be the, I guess, oxymercuration, demercuration version, I guess you could say. Anyway, so this is the acid-catalyzed hydration. And some mechanistic points here. We're going to form a functional group called an enol. Enols is basically an alkene, so alkene, plus alcohol, that's the COH. So you could imagine an enol would look something like that. And alcohol on an alkene, so enol. Enols are generally unstable, and they do this process called tautomerization. Tautomers are just essentially structural isomers that differ in the position of one double bond and one proton. They are isomers, okay? And they interconvert. So typically the keto form, so notice it's the difference in placement of the double bond and the proton. So this proton is now going to be over here. So there were 2 to begin with on the right side. So 1 and 2. Now there's 3. So we just move that proton over and then we move the double bond up into form a carbonyl essentially. So this would be the keto. And that's the enol. They go back and forth, but by far the keto is way more stable than the enol. There is a mechanism. We will teach it to you in Orgo 2. So for all intents and purposes, I want you to just know that we get to an enol. Imagine adding water across this alkyne, such that there's an H fragment on the less substituted side, the OH fragment on the more substituted side. You form an enol, that tautomerizes to a keto. Okay, generally that keto is always more preferred, more stable. Again, we will talk about this mechanism a little bit more in Orgo 2. Okay, so how do I kind of approach this problem? Well, if I had a generic terminal alkyne, doesn't have to be terminal. Okay, the reagents here is going to be mercury sulfate, so something like that, water, and sulfuric acid. Okay, so you can see kind of similar to the oxymercuration we saw before. So the first thing is we're going to form an enol at the more substituted position. So that would be that carbon of the alkyne, obviously. So we could imagine that we would form an enol. So we would put the OH at the more substituted side and the other proton at the less substituted side. This is the enol. And the enol tautomerizes preferentially more to the keto. So what does that look like? I'm going to put a carbonyl where the alcohol was. I'm going to bring one of the protons of the alcohol over to the right. Okay, and so that's kind of the keto version. So we are forming ketones and aldehydes from this reaction. So I think that's the biggest thing. So we just formed a ketone. Okay, so let's see an example of this. Okay, there is a bridged intermediate. I don't really care about that, but anyway, so here is another example. First step is kind of looking at the substitution of that double bond. The carbon on the left side of the alkene is clearly more substituted. There's that whole benzene fragment versus the right side that just has a proton. So we would imagine that the enol forms on the left. So this is my enol. And that is going to tautomerize to a ketone. So we just form a ketone. That's it. Let's try this with another example. Okay, so if I had this one, there is a potential for a mixture of products. So, same reagents. This is an asymmetric molecule, but the substitution around the carbons of the alkyne are the same. So therefore, there's no preference, and enols form at both sides, and we have to consider both. So for instance, if I considered, this green arrow, and I drew that enol, let's just kind of number the parent chain here, 4, 5, so there's 5. So 1, 2, 3, 4, 5. Let me just fill in the double bond. I could put the enol here versus the enol there. And both enols will readily tautomerize to the ketone. And notice that these are different structural isomers. One is at the 2 position, one's at the 3 position. So just be aware that both exist. And these would both be major. You would have 50% this, and you would have 50% that. So just keep in mind that if the substitution is the same and it's asymmetrical, you could get a mixture of products. But if it's, symmetrical, it's obviously 2 equivalents of the same thing. And if that's not obvious to you, let me just show you an example. Oops, not those arrows. So again, mercury sulfate, mercuric sulfate, sulfuric acid, water. So both of these carbons are, the same substitution. The molecule is symmetrical. The longest parent chain is a 6-carbon fragment. If I so the double bond is between 3 and 4. This enol versus 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oh, I added too many carbons up here. Versus this enol, they both tautomerize to the ketone. And notice both are at the 3 position. They're the same. Okay, so here you could just say this, 2 equivalents. Okay, so just to keep that in mind. Okay, so let's talk about the next reaction, so the hydroboration version of this. So we just saw, the acid-catalyzed hydration where it follows Markovnikov's rule. Let's just show the anti-Markovnikov version of that. So, oops, sorry, this is going to be 5B, I guess, so 5B. Okay, so this is still hydration of alkynes. But we'll talk, this is the hydroboration version. Oops. Hydroboration, oxidation. Okay, so instead of using, so we saw back with, I guess just an alkene, I'll bring that back. We saw we had borane, some inert solvent like THF. We saw we had sodium hydroxide and hydrogen peroxide. And our rationale back then was there's a BH2 fragment and an H fragment. This kind of reacted in a concerted mechanistic fashion such that the BH2 fragment aligned at the sterically unhindered side. And this was also a stereospecific reaction such that the BH2 and the H fragments will add at the same face because it's such a small molecule. So by that we meant that we had the BH2 and then the H would probably, add on the same face. This is not a chiral center, so nothing to really consider. But they do add syn to each other, since it's syn addition. So the same thing the step 2, sodium hydroxide and hydrogen peroxide, we don't teach the mechanism, but you can imagine that it just kind of erases the BH2. It's a source of OH, and that was our rationale for anti-Markovnikov, hydroboration conditions for alkenes. You can imagine we have the same situation happening with alkynes, however, slightly different reagent, but still kind of same principles here. So if I had a generic terminal alkyne, again, the new reagent here is going to be disec isoamyl borane. So you might see this as Ca2BH, same inert solvent as before, and then for step 2, same sodium hydroxide and hydrogen peroxide. So the only difference is the ligands, meaning the R groups. So here the 2 R groups are just H2. Here they are kind of bulky disec isoamyl groups. What does this molecule really look like? You should be aware of that. So isoamyl looks like this. So isoamyl, pretty bulky ligands, okay? I just want to point out this kind of borane functionality versus, this borane functionality for the alkenes. This enhances, the disec isoamyl one enhances the regioselectivity. That's why it's used. And again, the alcohol is going to end up on the less substituted side. So this is anti-Markovnikov addition. Based off of that idea of sterics, okay, the bulky isoamyl fragments want to go on the terminal side. Okay, so let's kind of see that. So I'm drawing all over the place here. But the enol that results would be a structure that looks like this. You remember that was the original proton. So the alcohol is on the less substituted side, position 2, and that readily tautomerizes to what we call an aldehyde, okay, because it's terminal. Okay, so 1, 2. So this was an aldehyde. Okay, so not too crazy. Enol still tautomerizes to a keto form, but since this is at the end and there's a proton present, we would call this an aldehyde. Let's kind of just talk about the mechanistic points. Again, we're not going to really emphasize the mechanism too much, but let's just talk mechanistic points here. So if I had kind of this structure, and I just want to show you this kind of mechanistic points. So these are the isoamyl groups, but I'm just going to call them Cia. The right side of the molecule, remember that's the right fragment, that's going to sterically align such that we are in the less sterically hindered side, where the terminal portion is just 1 proton. Whereas the less bulky side, this just single proton, is going to align at the bulky side. This is still a concerted mechanistic fashion where the the triple bond attacks the boron, and then this fragment comes back around. So again, I guess the result of this would be a structure that looks, actually I don't want to do it in line, I'm going to do it in line angle. A structure that looks like 2, and we get proton, SiA2, boron, R. We did the R already. This is the H. Okay, so the H and the BSiA2 group add such that the BSiA2 group is on the less sterically hindered side and the hydrogen is on the other side. And then you can imagine the next step, NaOH, H2O2, is just responsible for getting rid of that group and putting an alcohol at that position, okay, to form the enol. And then that enol, so actually I don't want to erase all of this. Anyway, so here, the enol will tautomerize to an aldehyde. It's still called the keto form, it's just specifically an aldehyde here. There we go. So that was tautomerization, and just know that we formed an aldehyde. Okay, not too bad. Maybe I'll do one more example where we have to consider asymmetric. So if I had something that looks like this. Okay, so this is 1, 2, 3, 4, 5. Just keep that in mind. Hydroboration conditions. Okay, so here, the substitution around these alkynes, well, both are looking primary like. They look the relative same. So we have to imagine both enols forming. Remember, this is the less sterically hindered, version. But in this case, it doesn't really look like there's a preference. Both are kind of primary like. Both have one R group attached. So I would have to consider 2, 3, 4, 5. 1, 2, 3, 4, 5. Both enols forming. The enol forming at 2, and then the enol forming at 3. And both tautomerize to the keto version. And in this case, you actually do get 2 structures. So you would have to put both of these structural isomers on your test. So something that looks like that. Both ketones. Okay, so keep that in mind. These are the products of that reaction. Let's do one where we actually have a steric argument, so just to compare that. So maybe I'll just do it quickly over here. Oops, let me do that, and then same conditions. So Cia, 2, BH, 2HF, 2, and NaOH, H2O2. Okay, so here there actually is kind of a steric side and a non-sterically hindered side. So exclusive enol is going to be on the right side. So if I were to number this, it's going to be exclusively at position 4. So the alkyne is between 3 and 4, and specifically the enol is at the less substituted side because clearly look at the sterics there. And then that is going to rapidly tautomerize to a terminal aldehyde at the 4 position. That's the only product for that. So look at the difference between both. Here, there really was no steric argument on the left. But on the right, we clearly have a steric argument. There is a secondary kind of branching group going on the left side. So anyway, that's the difference there. Okay, so now we're going to finally just close with these reductions of alkynes. There are specific reductions here that we need to be aware of. So we can either reduce an alkyne all the way to the alkane. That's the easiest one. So we'll just call this, I guess, reaction 6, catalytic reduction of alkynes. So this is going to be the strongest case. So reduction, remember, is gaining electrons, but specifically in organic chemistry, the definition of reduction is gaining CH bonds. Okay, so if we started with just a generic alkyne, and I used H2 and a metal catalyst such as platinum, palladium, or nickel. Any of these work. These are all options. Typically, we far often see palladium, but platinum and nickel also work. We don't know the mechanism, but you could just imagine that this is going to go all the way. Actually, I don't know what happened over here. Let me fix this. You can imagine that this alkyne goes all the way to an alkane. Notice all the protons we have gained. So this is a reduction, okay? So H2, platinum, palladium, nickel, do that. No mechanistic steps to be covered. So let's talk about this. at a terminal alkyne with a benzene. Remember, we do not touch those benzene bonds until orgo 2. But you can imagine that this 2-carbon substituent on the benzene aromatic ring is going to be a generic ethyl substituent once we reduce. Remember, we have now gained protons across that triple bond functionality. This is now an alkane. Ethyl benzene, essentially. Okay, so that is the strongest of the reductions. H2, platinum, palladium, nickel go from an alkyne all the way to an alkane. There are 2 other types. So that was number 6. Let's do another reduction, another catalytic reduction. So that was catalytic reduction of alkynes to alkanes. And now there's catalytic reduction to alkenes, and specifically 2 types. So cat reduction of alkynes to a Z alkene is what we're going to talk about now. Okay, so there is a specific catalyst to be used with this, and this is called Lindlar's catalyst. Lindlar's catalyst is just a combination of palladium with calcium carbonate and I guess lead. We do not need to know that. You just need to write the word Lindlar. But I just want to show you that it's a combination of a lot of crazy inorganic stuff. So it's those compounds over there. The only point is no mechanistic steps to be covered here, but we are going to get a Z alkene. So you can imagine if I start with some sort of internal alkyne like this, and I use H2, and I'm going to write the word Lindlar's, we would expect an alkene such that the R groups end up on the same face. So that is a Z alkene. Remember that nomenclature. Okay, so an example of this would be if I had maybe this structure. Okay, and I do H2 and Lindlar's. 1, 2, 3, 4, 5, 6. So I could draw a 1, but keep in mind 3 and 4 is actually where the Z needs to happen. So 1, 2, 3, 4, 5, 6. So this is the 3, 4 is where the Z situation needs to happen. Okay, so it's something as simple as that. All right. Okay. 1, 2, 3, 4, 5, 6. Great. Now there's one more step. Okay, so I guess I'll just on the next page. 8, last catalytic reduction. So cat reduction of alkynes. You can imagine now to E alkene, so a different reagent. So here, if I had another internal alkyne, the reagent here is pure sodium metal, sometimes denoted with this little degree sign. That's sodium not. It means pure elemental sodium with an electron, 1 electron available. This would go to the trans fashion, the E alkene, okay? So again, here's an example, pretty simple, no mechanistic steps to be covered here. But if I had this type of, alkyne, and I use the pure sodium metal and liquid ammonia, you can imagine 1, 2, 3, 4, 5. So this is 7 carbon chain, 3, 4, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. E alkene. That's simple. And that is a great summary of your organic reactions. Good luck.